Assalamu alaikum students. So today we are going to solve some problems related to our isentropic compressible flow through different geometries. And first, the problem. Let's read out the statement. A statement first. This is the problem in 11.5 from your Munson book. And in this problem, an ideal gas is to flow isentropically from a large tank where air is maintained at a temperature and pressure of 59 degree Fahrenheit and 80 pound per square inch absolute pressure to standard atmospheric discharge conditions. So there is some sort of a gas inside a tank, and then that gas is exited into the atmosphere, and here the gas is pressurized. So there is a pressurized gas inside this container, and that is being exited to the atmosphere into the standard atmospheric discharge condition. So this is our discharge. This will be our discharge. So describe in general terms the kind of duct involved and determine the duct exit Mach number and the velocity in feet per seconds if the gas is air. So what we are going to do, we are going to find the Mach number and the velocity, and then by these two findings, after finding the Mach number and the velocity, we will determine that which type of duct was involved for this whole scenario. So first we are given some data in this problem, so let's use that data and find some unknowns that we can. So first of all, we are going to use this table, and this table is a very useful one. This is the table C.1 that is given in the appendix of this book, and this table gives you the properties of US standard atmosphere in the British gravity units. So here for different altitudes, temperature and temperature, you can find the pressure, density and the dynamic viscosity and the acceleration due to gravity for different gases. No, sorry, for the US standard atmosphere. So the temperature, pressure at different altitudes in this table. So what we are going to use this table for, we are going to see that what is our atmospheric temperature. So for 59 degree Fahrenheit, so at 59 degree Fahrenheit, this is 59 degree Fahrenheit, the atmospheric temperature will be 14.696. so P right here will be 14.696, and the P naught that is given in this statement, P naught is 80 psi absolute. So we now know our P and P naught, and P here is this pressure is the exit pressure. This is the exit pressure. So again, let's revisit the scenario. This was, let's say this is our tank and this was our discharge. So the discharge pressure is this one, the one that we read from the table. So here this is the P exit, if you would like to say, that is 14.696 psi, and inside the container the pressure was 80 psi. So we are going to take their ratio, and then we are going to use the table to read out the other values. So sorry, not the table but the graph that we mentioned previously in the lecture, from which we can get the values of pressure over the stagnation pressure, temperature over the stagnation temperature, and other values like the Mach number. So we now know our P over P naught, and the P over P naught will be 14.696 divided by the 80 pound per square inch pressure, and this ratio will come out to be 0.1838. So now we are going to use this value, that is 0.1838, and use that in the graph to find other values. So you can also use this equation, but in this equation, from this equation we can also find the Mach number. So it will be a tedious process of lengthy calculations, and we can also use this equation to find our exit temperature. But again, for that we need to find the Mach number, and again this will involve calculations. And this, if you require density, but this equation will not be used in this problem because it is not required. So first, what we are going to do, we are going to use this value in the graph that we have, because this is the simple method. And this graph, just to remind you, this graph is for ideal gas with a specific heat ratio value of 1.4, K is equal to 1.4. So this graph will specifically be used for air, whose values, specific heat capacity ratio value is 1.4. So this graph will be used whenever we are dealing with air. Other than that, we are going to use the equations that are mentioned right here to find these values. So now we know our P over P naught value, and to mark it on this graph, this is where our P over P naught value will lie. So this is our P over P naught value line, and here this is where our 0.1838 will lie right here. So this is 0.18 that is mentioned right here. So from correspondingly to this point, we are going to read our Mach number, and this will be our Mach number. This point, this will be our Mach number. So our Mach number will come out to be approximately, looking from here, it will come out to be 1.8. So this is our Mach number. We can similarly approximate the value of T over T naught from here, and it will come out to be just right here. If we draw the line, yes, it will come out just right here, and that will be T over T naught will be equal to almost 0.62 approximately. So this is our values that is required, and now we are going to find what is required. So we have already known the exit Mach number, that is 1.8 from this graph, and now we are going to find the exit velocity, and for that we are going to use the Mach number equation, that Mach number is equal to V over C. So this is our exit velocity now, and we need to find this. So rearranging this equation, this will give us the Mach number into the speed of sound, and this can be written as under root R T K. We are familiar with this equation. So now our Mach number is known. We can find the universal gas constant value for air from the table given at the end of this book, and that value is R is equal to 1716 foot-pound divided by slug into degree Rankines. So this is the value of R. We can find the exit temperature from this formula, and the K is already 1.4, so we know that. So let's find this exit temperature first. Let's give some space. So let's use this equation. T is equal to T naught is given, which is 59, and this ratio is 0.62. But this 59 right here is not the absolute temperature. This is in degree Fahrenheit, and we need to convert this into degree Rankines. So what we need to do, we need to add this with approximately, for degree Rankines, this will come out to be 59 plus 460. So So this will gives us the temperature in absolute terms, and the value will be in degree rankings. This will come out to be in degree ranking. So from here we can find our exit temperature by calculating these values. So the exit temperature will also come out to be in absolute units. So now we know our Mach number, we know our values of R. From this equation we will know the exit temperature, and the K value is 1.4, which is already known. So we will get our exit temperature also. So exit temperature, and from this equation we can find our exit velocity, that will come out to be in foot per second. So this will be our exit velocity. So our problem is solved, but not all the way. What we need to do is to describe in general terms the kind of duct involved. So what kind of duct will be involved if the flow is of Mach number 1.8? So 1.8 is which one flow that can be? One is sonic, above one is hypersonic and supersonic. So MA Mach number, that is Mach number is 1.8, so that is a supersonic flow. And if you remember our previous lecture in which we were discussing our diverging, converging, diverging duct, and in that duct we said that whenever a supersonic flow passes through this duct, its velocity will increase. The change in velocity will be greater than 0. So the velocity will stay supersonic, it will increase. So in this case we can also say that the nozzle that is involved is a converging diverging nozzle. The nozzle that is involved is a converging diverging one, because the flow is supersonic. And if let's say that we draw the converging diverging nozzle, let's say that this sort of a nozzle involved. So if the flow was subsonic in this regime, let's say it was Mach less than 1, when a subsonic flow passes through a diverging portion, it will increase in velocity, and let's say that it will increase, and if it crosses the Mach number 1 regime, then in the diverging portion it will remain supersonic. Because this is what we studied in this scenario in our previous lecture, if you recall that. So now we can say that the duct involved that was required in this problem is a converging diverging one, so that flow can be maintained as supersonic, because the Mach number that we found in this problem was 1.8, which is in the supersonic regime. So we can safely say that the duct involved is a converging diverging one. Okay, so now let's look at another problem, and in this problem again we have an ideal gas, so that is flowing isentropically through a converging diverging nozzle. So again we have a converging and a diverging nozzle case. At a section in a converging portion of the nozzle, the area is 0.1 meter square. So this is the converging portion of this nozzle, that is section 1, whose area is 0.1 meter square. The pressure there is 600 kilopascal absolute. T1, that is the temperature at this converging portion, is 20 degrees centigrade, and the Mach number is also given, so that is 0.6. So all the values almost are given at the section 1. We just have to convert this temperature into absolute temperature into kelvins. So for section 2 in the diverging part, so this is the diverging part, section 2 in the diverging part of the nozzle, determine A2, P2 and T2, and the Mach number is given, that is 3.0, and the gas is air, so the ideal gas is air, so the value of K will be again 1.4, that is our specific heat capacity ratio. So the Mach number is very high at section 2, so we need to find the area at section 2, the pressure at section 2, and the temperature at section 2. So now what we are going to do, we are going to use our equations, and then we are going to use that graph that we used in the previous problem. So this is also an equation, that is equation 11.7 in your compressible flows chapter, and this ratio, the area over the critical area ratio, is also given in relation to the Mach number, and this equation can be used to find the critical area that is under choking condition. Or what we need to do, we can also use this equation now to find the area A2, because we can we have the Mach number, we have the Mach number. So the Mach number for both the sections, here the Mach number is 0.6 and here it is 3.0. so this is our Mach number, and what we are going to do, we are going to find the A over A star from the graph for this scenario, and then our A over A star for this scenario. So what we will get A1 or A star by reading the values from the graph for this Mach number, and A2 or A star by reading the values from the graph for this Mach number. So let's do that first. Similarly, we are also going to use these equations. We will come back to these equations, that is for pressure and temperature, but first we are going to use this graph that we have, and first we are going to mark our Mach 0.6 that lies over here, and for that Mach number, our A1 or A star value will be read from the right vertical line that is given in this graph. So that value will come out to be this, that is A1 over A star. So A1 over A star is just approximately 1.2, let's say, and then we can also read the other values, that is for P over P naught, but we will use these values a little bit later in this problem. Next we are going to mark our Mach 3.0 on this graph, that is this point. This is Mach 3.0, and correspondingly our area A2 over A naught that is required. So this will be this is for our pressure, we need value of our area, and that will come out to be this, that is this area A2 or A naught will come out to be approximately, let's say 4. So this is our A2 or A star. So we have now gotten these values, and let's use these values in equations to find A2, because we know A1, we know this ratio. So now let's use these values, and by rearranging this equation for this first and then for this value first. So now let's rearrange this equation and write this equation as A1 over A star. So A1 over A star will be equal to the right hand side that is given. I will just draw their brackets, and then the rest is this given in the graph. Similarly, A2 or A critical will be equal to the same, just the Mach number in this case will be 1 over Mach number 1, and in this case will be 1 over the Mach number 2. So again we can now relate these two equations, because these two equations have one thing in common, and this is the A star. So if I rearrange this equation for A star, or let's say I rearrange this one, so A star will be equal to A2 divided by this whole value, and let's say I call this whole dy, so A2 over y. So now I can put the A star value in this equation right here. So let's put that value here. And now I can write this as a1 divided by a2 over y. So this is again 1. Let's call this whole right here x. So now I have these two equations in terms of a1 and a2, and now I can further rearrange this as a1 over a2 is equal to this is our x, and if I shift the y the other words, this will be our y. So now I can again rearrange this equation, and this equation I need the area a2 because this is my unknown. So for a2 this equation will become as a2 is equal to a1 into y over x. And as you remember, the y was the value for our a2 over a star, that was y, and the xy x was the equal to a1 over a star, and we can know their values from the graph that is given. So we will actually get the values of y and x, and then I can find my a2. So a2 or a star will be equal to we have read it from the table, and that was somewhat around 4. So that was 4. So here in terms of y I will put 4, and then our a1 or a star was given as this value right here, and it was equal to 1.2. So now I will put 1.2 instead of x, 1.2. So now I have my equation for a2, and I can find a2 because I know a1 that is given in the statement, and a1 right here is 0.1 meter square. So by putting 0.1 meter square here, so I can find my area a2 in terms of meter square. So this is our area that was required, a2. Now we need to find p2 and t2 also. So let's do that by rearranging the other two equations that are given to us. So just by doing the same exercise, we are going to find p1 over p0 for Mach number 1. This was our Mach number 1. From this graph, and p1 or p0 will come out to be 0. Let's say if we read it from here p1 or p0, this was our Mach number, and this line crossed this just right here. So p1 over p0 is approximately equal to 0.78. Similarly, p2 over p0 will be given to us by this line, and this line is coinciding with this right here. So it is very small, and it will be approximately equal to 0.03, let's say. So these are approximately equal to these values. Now I can apply the same method that I did for this right here. So here p1 over p0 will be equal to this value, and p2 over p0 will again be equal to this value. The only difference will be the Mach number, in which case it will be 1, and here it will be 2 in this equation. So again this is there is one value that is common right here in both equations, that is p0. So let's rearrange this equation for p0, and it will come out to be p0 is equal to p2 over, and let's call this whole y. This is y, and again please note that y is equal to p2 over p0. So we will have to put this left hand side again, and once we rearrange it for p2. So I have rearranged this equation into this. So now let's use this equation and put it in the one at the top, and let's say that here p1 over p0 was equal to x. So here p1 over P naught. So now let's put the value of P naught here, and P naught is equal to P2 over Y. We know that from this equation. So let's rearrange it for P1 over P2 will be equal to X over Y. So now I can rearrange this equation for P2, and P2 will come out to be P1 into Y over X, and I know that P2 is equal to P1 into Y is equal to P2 over P naught, P2 over P naught divided by the X, that is P1 over P naught. So now I know my values for these two, and I can find my pressure at P2. So this will come out to be P1 is 600 kilopascals absolute pressure into P2 over P naught is 0.03, and P1 over P naught is 0.78. So from here I can find my P2 in terms of kilopascals. That will be the absolute pressure. So this is my P2 that was required. So now I have only one unknown left, and that unknown is my temperature T2. So by doing the same exercise for the equation that is given to us for temperature and the stagnation temperature and the Mach number, we can actually find our T2 by doing the same exercise again. So let's do that again, and I can arrange this equation again for T1 over T naught, and that will be equal to the right hand side that is given here. Here the Mach number will be MA1. I will call this again X, and then T2 over T naught, and this will again be equal to Mach number 2, and here it is will be equal to Y. So T1 over T naught can be read from this right here, from this point right here for Mach number 0.6, and its value will come out to be this, and it is approximately equal to 0.93, and then T2 over T naught will be read from here, and it will come out to be approximately equal to this point right here. This right here is T2 over T naught, and it will be approximately equal to 0. Let's say just about 35. So let's about say 0.36. So now there is again T naught common. So let's rearrange this equation for T naught, and it will come out to be T2 over Y will be equal to T naught. So let's erase this equation. And now let's write T1 divided by, let's put T naught here, the value of T naught, and it will come out to be T2 over Y is equal to X. And again, after rearranging this equation, it will come out to be T1 over T2 is equal to X over Y. And for rearranging it for T2, it will come out to be T1 into Y over X. One thing that we have to do is to convert the temperature into absolute temperature by adding 273 to it. So this will be our T1, and it will be in kelvins. So Y is again our ratio T2 over T naught, and X is our ratio T1 over T naught, and I know their values. This value is 0.36 and this value is 0.93, and T1 is given, so we can find our temperature T2, that will be in kelvins, the absolute temperature. So by doing this, we will have our temperature T2 that was required. So now our problem is solved. We have established an equation for A2, P2 and T2, and by putting in the corresponding values, you can find these values by yourself. So let's look at another problem, and in this problem we are given a statement in which the upstream of a throat of an isentropic converging diverging nozzle at section 1 we are given velocity, pressure and temperature. If the discharge flow is supersonic, that is the discharge flow is supersonic and the throat area is 0.1 meter per second, determine the mass flow rate in kilogram per second for flow of air. So we have a converging diverging nozzle, and upstream of this converging nozzle, let's say this is the section 1, and here we are given velocity V1, pressure P1 and temperature T1, and they are saying that at the throat, this is the throat, the flow is supersonic and only the area of this region is given. So what we are going to do, we are going to find the mass flow rate for the flow. Here at the throat the flow is supersonic as it is mentioned. So what we are going to do, we are going to further elucidate the condition of this flow by finding the Mach number at this section 1. We can find the Mach number of this section 1 because we are given the velocity and the temperature. This is what is required, because if we look at the Mach number, then it is let's say V1 over C, and we know that V1 over C is equal to the universal gas constant, the absolute temperature T1, and K, which will be in this case it is air, so we also know the value of K. So let's put the values in, and we will get 150 meter per second divided by under root the universal gas constant value, that is 286, and its units are Newton meter per kilogram into degree kelvins. So this is the value of R. T1 is given as 20 degree C. We will convert it into absolute temperature. It will come out to be 293 kelvins and into 1.4. So by solving this, if you solve this, the Mach number comes out to be 0.43 approximately. So this shows that at this region, the flow is subsonic. The flow is subsonic. So what we are going to do, we are going to make an assumption for this problem, and our assumption will be that since the flow is subsonic at the upstream of this nozzle and it is being accelerated, so what we are going to do, we are going to consider this flow at this region, at the throat. We are going to say that the flow is choked. The flow is choked, and the Mach number, as we know, it is 0.43. Let's write it down. So now we are going to solve this problem by taking the values of section 1, and at section 2 we are going to use all the formulas that were given for the choked flow, and that in case also for air. So from that we are going to find our mass flow rate, and our mass flow rate will be m dot is equal to rho, the critical density, rho A, the critical area, and the critical velocity. So this is what we are going to do. We are going to find these values. So first of all, what we are going to do, we are going to use some equations. So let's look at them. We are going to use this equation, the pressure or the stagnation pressure, the temperature or the stagnation temperature, and then these two formulas for our pressure at the critical point, and that is the throat right here, and the stagnation pressure and the critical temperature over the stagnation temperature. Please note one thing, that we are not given the stagnation properties of pressure and temperature, so we are going to find that first from these formulas and then put them right here to find the stagnation pressure and temperature. So let's do that, and the stagnation density will also be required. The critical density, and the critical density rho will be found out from this formula, that is P over R T star. So we are going to use this formula to find the stagnation density and to calculate the mass flow rate. So let's do that first. We are going to use this let's use this equation first. The pressure or the stagnation pressure on P1 or P0 will be equal to this value. I'm going to just again call this X, and what I'm going to do, I'm going to arrange this formula for P0 because I'm interested in finding that P1 is given in the statement, that is 100 kilopascal is the absolute pressure. So P0 will be equal to P1 over X, and X, as you know, is P1 over P0, and we can see this value from the graph that we saw in the previous two problems. And for the Mach number, 0.43, we will read the value of P1 over P0, and if we use the graph, the P1 over P0 value will come out to be approximately 0.8. So this will be our value of P1 over P0, and we will solve this equation for P0. We will get our value of P0 in terms of kilopascals, and that will be also the absolute pressure. So we will get our value P0 like this, and similarly doing the same for T1 over T0, we are going to use our Mach number and find the value of that is T1 over T0 is equal to this equation, and let's call this whole values inside the bracket as y, and we will arrange this equation for T1 over y, and y, as you know, is equal to T1 over T0, and its value for Mach number 0.43 in the graph will come out to be T0 T1 over, and it will come out to be approximately 0.9. So this is how we are going to find T0, and that also in terms of absolute temperature, and we are going to put T1 as 293 kelvins, not 20 degrees C, because we are talking about absolute values of temperature and pressure. So that's how we are going to find our temperature and pressure, that stagnation temperature and pressure. Now we are going to use that stagnation temperature and pressure and put them in these formulas that again will be in terms of kelvins. So now I am going to use these two equations, and P star over P0 is equal to 0.528. We know that from our textbook, so I will put the values of P0 and we will get P star. Similarly, that will be in kilopascals, absolute pressure. Similarly, I am going to use T star over T0, and I'm going to multiply T0 right here, and I will get the values in Kelvin. So now I know my values for pressure and temperature. These are the critical pressure and critical temperature. So now what I am going to do, I know the area, I know the pressure, so I need to find the velocity as well. So for that purpose I am going to use the formula of so first let's say we also find the critical density as well, and the critical density can be found by this formula, because now we know the critical pressure, the critical temperature, and the value of R is known. So we will also have our density as well. So we have our density, we have our area, we need to find the critical velocity, and that critical velocity can be found by using our formula, that is that the Mach number is equal to V over C. And if we rearrange this equation, so let's say that V star and C will come out to be V star over under root R, that is the critical temperature, and the value K. But we don't know the Mach number at this point, but since we have considered the choked condition, we have said that the flow is choked. So you know that what does that mean. In this scenario, the Mach number will equal to 1. So by putting the Mach number equal to 1, we can actually find our V star. So now by just solving this equation and putting the Mach number equal to 1, because we have considered the flow is choked. So we can find our value of V star, and it will come out to be meter per second. So from this equation we can actually find our critical velocity, and then using this equation right here we will actually find our mass flow rate in kilograms per second. So this is how we are going to solve this problem, by first finding the Mach number at section 1, and then considering the flow is choked because the flow is being accelerated from subsonic to supersonic, and by taking the critical area and finding the critical density and the velocity from these equations, and then finding the stagnation temperature and pressures, we can actually calculate all the values and find our mass flow rate that was required for this scenario. And the one assumption that we did was that we considered the flow is choked, and by doing so we were able to solve this problem.